So now we are asked to evaluate this line integral, but we have a suspect that this line integral is path independent. So in order for that to be true, we need that to have f equal to the gradient of a scalar function f. So in order for this to be real, we will need that f1 will be equal to the derivative of f with respect of x, f2 will be equal to the derivative of, f with respect of y, and f3 equals to the derivative of f with respect of z. And we know that f is equal to ex squared plus y squared plus z squared times x, y, z. So we can make our guess, and suppose that f will be equal to the integral of f1 with respect of dx. Hence we will have the integral of x times ex squared plus y squared plus z squared dx. And it's easy to see that this integral will be equal to ex squared plus y squared plus z squared times 1/2. Okay, plus another function that will be dependent on y and z. Okay, now we can make another guess and said that f will be equal to f2 now integrated with respect of y. So we'll have something like this, and the result will be something similar to this one. Okay, and our final guess, saying that now we will be integrating the f3, but now with respect of z, and we will have something like this. And we will obtain something really similar to what we had already. Just to make this something different, this is here, u1 and u2. Okay, well, now we will be saying, well, if this is true, then 1/2 of ex squared plus y squared plus z squared plus g0 depending of yz will be equal to 1/2 of ex squared plus y squared plus z squared g1 exit. And so something like this. Right. Okay, so we can see that these three sections are the same. Hence, we cannot suppose that g0 is equal to u1 equal to u2, but this is equal to 0. Hence, the scalar function would be equal to 1/2 of ex squared plus y squared plus z squared. But this has not yet tell us if it's true that f is equal to the gradient of f. However, we can make these calculations. We know that the gradient of f is equal to a vector where we have df with respect of x, df with respect of y, and df with respect of z. So we can make the calculation and obtain the derivative of this function. So we will have something like this. Over 2 y over 2 ex squared plus y squared plus x squared, comma 2z over 2 ex squared plus y squared plus z squared. And these two will be eliminated, and we will get ex squared plus y squared plus z squared times x comma y comma z. And this is indeed equal to f. You will see it up here. Here it is. So it is path independent. Yeah. Okay, so this is true. So now we can say that the integral can be evaluated as f evaluated, and I'm gonna have to check this at f at b minus f at a. Alright, and from the original integral we see that a is equal to 1 1 1 comma 1 comma 0, and oh no, that will be, if I'm wrong, sorry, this will not be a, this will be v, and a will be equal to 0 comma 0 comma 0 exactly. Then the integral can be evaluated as f at 1 comma 1 comma 0, which was b. Sounds good. Let me just check it again. Okay, minus f evaluated at 0 comma 0 comma 0. Right? Yeah. It's easy as that. Then we have, so I was saying f will be equal to 1/2 of e 1 squared plus 1 squared plus 0 squared minus 1/2 of e to the 0 squared plus 0 squared plus 0 squared. Alright, and this will be given us 1/2 of e 1 plus 1 squared minus 1/2 of e to the 0, which will be equal to 1/2 of e squared minus 1/2. So it's equal to, then e squared minus 1, and that's the result. And as easy as that, we can evaluate a path independent line integral.